In 1897, a Scottish immigrant named Alexander Winton was about to make a decision that would accidentally trigger one of the most dramatic industrial transformations in American history. But here's the twist. The company that started this revolution would be completely erased by the very transformation it created, disappearing so thoroughly that most people have never heard the name that helped reshape an entire continent's transportation system. The Pioneer. Alexander Winton should have been satisfied. By 1899, his Winton Motor Carriage Company in Cleveland was producing roughly 25 cars per week and had become one of the largest gasoline automobile manufacturers in the United States. This was no small achievement in an industry that barely existed a decade earlier. Winton had established himself as one of America's earliest automobile pioneers, building handcrafted luxury vehicles when cars were still experimental machines that most people viewed as dangerous curiosities. The early automobile industry was a wild frontier of inventors and entrepreneurs, each trying to solve the fundamental problems of making horseless carriages reliable enough for wealthy customers to actually purchase. Winton's cars sold for $1,000 to $2,000 each, the equivalent of tens of thousands of dollars today, and attracted buyers like socialite Lars Anderson and businessman Robert Allison, who treated these painted, padded machines with their leather roofs and gas lamps as technological marvels rather than practical transportation. But the industry was rapidly filling with competitors. Companies like Oldsmobile, Cadillac, and Ford were entering the market with their own designs, and the race to capture market share was intensifying. Smart money suggested that successful manufacturers should focus entirely on automobile production, expand their facilities, and grab as much of the exploding market as possible while the opportunity existed. The automobile represented the future of personal transportation, and companies that dominated early would likely control the industry for decades. Yet the Scottish immigrant who had built his fortune first on bicycles and then on motor cars was growing restless with his own success. While his competitors celebrated their expanding automobile sales and invested everything in meeting the surging demand for personal transportation, Winton was becoming obsessed with something far more ambitious and infinitely more dangerous to his established business. He spent his evenings in his Cleveland workshops sketching designs for massive internal combustion engines that could power ships, factories, and heavy machinery, applications that had nothing to do with the automobile market that was making him wealthy. The decision represented a staggering gamble. Winton's automobile company was generating substantial profits in a rapidly expanding market, with customers who couldn't get enough of his innovative vehicles. Any rational businessman would have doubled down on automobile production, expanded manufacturing capacity, and captured as much market share as possible while the industry was still young. Instead, Winton began quietly diverting resources toward experimental engine designs that most manufacturers considered completely impractical and commercially impossible. But Winton had identified an opportunity that dwarfed even the automobile revolution: engines in a steam-powered world. At the dawn of the 20th century, virtually everything that moved or generated power in the United States ran on steam. The technology dominated American industry so completely that alternatives seemed almost unimaginable. Steam locomotives were expensive to maintain, required large crews, and burned enormous quantities of coal even when standing idle. Ships consumed tons of coal to heat massive boilers that drove paddle wheels and propellers. Factories operated with complex systems of belts and pulleys powered by central steam engines that required constant attention and fuel. Winton believed that internal combustion engines could replace all of it, but the challenge was staggering. Early internal combustion engines were mechanically unreliable, impossibly complex to manufacture at industrial scale, and prone to catastrophic failures that made them unsuitable for critical applications. Most engineers dismissed the idea of building engines powerful enough to replace steam as a fantasy that would bankrupt any company foolish enough to attempt it. In 1912, Winton established an engine division within his automobile company dedicated to developing large internal combustion engines for marine and industrial applications. The timing was crucial. Rudolf Diesel's compression ignition engine had been proven in Europe, and while a few American pioneers had begun producing diesel engines domestically, the technology remained a niche curiosity used mainly in heavy industrial and marine applications. The early experiments were brutal and expensive. Diesel technology presented engineering challenges that were fundamentally different from anything Winton's team had encountered in automobile engines. Where gasoline engines used spark plugs to ignite fuel, diesel engines relied on compression ignition, squeezing air so tightly that it became hot enough to ignite fuel injected at precisely the right moment. The pressures involved were enormous, far beyond what gasoline engines experienced, and the mechanical stresses threatened to destroy any engine not built to withstand forces that pushed the limits of available materials. Winton's engineers struggled with fuel injection systems that clogged constantly, shutting down engines without warning during critical tests. The injection pumps had to deliver fuel at pressures that exceeded anything used in gasoline engines, and the precision required was extraordinary. Fuel had to be injected at exactly the right moment in the compression cycle, or the engine would either fail to start or destroy itself. Early injection systems were crude and inconsistent, causing engines to run roughly when they ran at all. Combustion chambers cracked under the intense pressure and heat of diesel combustion, destroying expensive prototypes after just hours of operation. The temperatures inside diesel cylinders were far higher than in gasoline engines, and the rapid pressure changes during combustion created stresses that fractured cylinder heads and cracked engine blocks. Each failure meant weeks of analysis to understand what had gone wrong, followed by months of redesigning and rebuilding components that might fail again in different ways. Diesel engines operated at much higher pressures and temperatures than gasoline engines, creating severe thermal stresses that early cooling systems struggled to manage. Radiators designed for automobiles were completely inadequate for industrial diesel engines, and designing effective cooling systems required understanding heat transfer principles that were still being developed. Engines would run for short periods before overheating, warping cylinder heads, and seizing pistons in their cylinders. Each prototype required months of painstaking development and testing before it could run for more than a few hours without breaking down, and most failed long before reaching anything resembling commercial reliability. The development process was a grinding series of failures, modifications, and incremental improvements that consumed enormous amounts of time and money while producing engines that were still too unreliable for commercial use. Winton was essentially trying to solve a dozen different engineering problems simultaneously, any one of which could have destroyed the entire project. But Winton kept pushing forward, gradually building engines powerful enough for marine vessels and industrial installations. By 1913, Winton's engineers had developed several large experimental engines for marine applications, leading to limited production later in the decade. Within 3 years, Winton engines were appearing in ships across the Great Lakes and along the American coastline, proving that the technology could work reliably in demanding commercial applications. But the real opportunity lay somewhere else entirely. This technology might not just power ships, it could transform the largest transportation industry in America. The railroad industry represented a massive industrial empire that moved freight and passengers across the continent, using technology that had remained essentially unchanged for decades. American railroads operated over 250,000 miles of track, employed over 2 million workers, and represented one of the largest concentrations of capital and industrial infrastructure in the world. The entire system ran on steam power, and the operational costs were becoming crushing burdens for railroad companies. Steam locomotives required crews of skilled workers, engineers who controlled the engines, and firemen who shoveled coal into fireboxes to maintain steam pressure. These workers commanded high wages because their skills were specialized and dangerous, and railroads needed thousands of them to keep their fleets operating. The locomotives burned enormous quantities of coal, whether they were hauling freight or sitting idle in rail yards, because maintaining steam pressure required continuous combustion. A typical freight locomotive consumed several tons of coal per day, even when not working, and the fuel costs represented a major expense for every railroad company. Most critically, steam locomotives were slow to start and required extensive preparation before they could operate. Building steam pressure from a cold start could take hours, making it impossible to respond quickly to changing transportation demands. The locomotives needed constant attention from experienced crews who understood the complex systems that kept the massive machines running safely. Operational mistakes could result in boiler explosions that killed crews and destroyed expensive equipment. Railroad executives across the country were quietly growing desperate for alternatives that could reduce their crushing operational costs and improve the reliability of their locomotive fleets. If diesel engines could be made powerful enough and reliable enough to haul trains, they could potentially transform the economics of railroad operation. Diesel locomotives would require smaller crews, consume fuel only when actually working, and start instantly without the lengthy preparation required by steam engines. Inside Winton's Cleveland workshops, the technology that could eventually replace this entire system was starting to take shape. The company's large internal combustion engines were becoming more reliable, more powerful, and easier to manufacture. Winton engineers had begun solving many of the fundamental problems that had plagued early diesel designs, developing fuel injection systems that worked consistently and cooling systems that could handle sustained high-power operation. By the early 1920s, Winton was producing gasoline engines for rail motor cars, laying the groundwork for the company's later diesel designs. But Winton faced a fundamental problem that threatened to prevent the company from capitalizing on the revolution it was creating. Building locomotives required manufacturing capabilities, distribution networks, and customer relationships that were completely different from engine manufacturing. Winton had mastered diesel engine technology, but transforming that expertise into a successful locomotive business would require resources and infrastructure that were far beyond what a Cleveland engine manufacturer could develop independently. The solution emerged from an unexpected partnership. In 1922, Harold Hamilton and Paul Turner founded the Electromotive Engineering Corporation in Cleveland. The company soon reorganized as the Electromotive Corporation, focusing on gasoline-electric rail motor cars. Hamilton and Turner weren't engine manufacturers, they were specialists in designing and marketing innovative rail vehicles, contracting with other companies to supply engines and electrical equipment. By 1923, Electromotive had begun purchasing engines from Winton for their rail motor cars, creating a collaboration that would eventually reshape the entire railroad industry. The partnership caught the attention of General Motors executives who were searching for new markets to expand their industrial empire beyond automobiles. GM had built its fortune on personal transportation, but company leadership recognized that the automotive market would eventually mature and growth would slow. They needed to identify emerging technologies and markets that could provide the next wave of massive expansion, and diesel locomotives represented exactly the kind of opportunity GM was seeking. A huge, underserved market where superior technology could displace entrenched competitors. On December 31, 1930, General Motors made a move that would transform American transportation. The company acquired both the Electromotive Corporation and the Winton Engine Company, bringing together the railroad industry expertise and the diesel engine technology that would power the coming revolution. GM executives understood that they were positioning themselves to dominate what could become a transportation market as large as the automobile industry itself. GM began investing heavily in locomotive development, using Winton's diesel engines as the foundation for locomotives that could outperform steam in efficiency, reliability, and operating cost. By 1934, engineers from Winton working alongside General Motors' research division completed development of the 201A diesel engine, a revolutionary two-stroke design that would transform locomotive power. The 201A featured advanced welded steel construction, uniflow scavenging with intake ports in the cylinder walls and exhaust valves in the cylinder heads, and mechanical unit fuel injection that provided precise fuel delivery under all operating conditions. A prototype version of Winton's new diesel engine appeared at the 1933 Chicago World's Fair, but the completed 201A would make its true debut the following year in the Pioneer Zephyr. Ralph Budd, president of the Chicago, Burlington, and Quincy Railroad, witnessed the engine's smooth, reliable operation and immediately recognized its potential for railroad applications. Budd commissioned the construction of a revolutionary streamlined passenger train powered by a single Winton 201 series diesel engine, a gleaming stainless steel vehicle that would become known as the Pioneer Zephyr. On May 26, 1934, the Pioneer Zephyr completed a demonstration that electrified the railroad industry and announced the arrival of a new era in American transportation. The train completed a record-breaking 1,015-mile nonstop run, from Denver to Chicago in just 13 hours and 5 minutes, averaging nearly 78 miles per hour for the entire journey while consuming a fraction of the fuel that a steam locomotive would have required for the same trip. The Denver-Chicago run was front-page news across the country. Newspapers from coast to coast reported on the gleaming train that had crossed the continent at unprecedented speed while burning a tiny fraction of the fuel required by steam locomotives. Radio stations broadcast updates during the run, and crowds gathered at stations along the route to witness the silver train flash past at speeds that seemed impossible for railroad equipment. The demonstration captured the public imagination and announced that transportation technology was entering a new era. Railroad executives who had dismissed diesel power as impractical suddenly realized that the future of their industry had fundamentally changed. The Zephyr had demonstrated that a single diesel engine could haul a passenger train at speeds that rivaled the fastest steam locomotives, while requiring only one engineer to operate and consuming fuel only when actually working. The implications were staggering. If diesel technology could be scaled up to handle freight trains, it could potentially eliminate the massive operational costs that were crushing railroad profitability. Orders for diesel-powered trains began pouring in from railroad companies across the country. The Santa Fe Railway ordered diesel locomotives for passenger service. The Baltimore and Ohio commissioned diesel-powered trains for their premier passenger routes. Even conservative freight railroads began experimenting with diesel switcher locomotives for yard operations, where the ability to start instantly and operate efficiently at low speeds provided obvious advantages over steam power. GM's electromotive division found itself at the center of a technological revolution that was reshaping American transportation. GM soon became Winton's largest customer, purchasing a growing share of the company's diesel engine production for locomotive development. The Cleveland company that had pioneered American diesel technology was becoming increasingly dependent on its relationship with the automotive giant. As GM's locomotive business expanded during the 1930s, diesel locomotives proved themselves in passenger service and switching operations. Their dominance in heavy freight would come in the following decade. Passenger services found that diesel power provided smoother, quieter operation that enhanced the travel experience. Most importantly, railroad maintenance departments realized that diesel locomotives required far less servicing than steam engines, reducing operational costs and improving equipment availability. By the late 1930s, General Motors had become the dominant force in American locomotive manufacturing, with electromotive leading the industry in diesel technology and production volume. The success was built entirely on Winton's diesel engines, but the Cleveland company was increasingly invisible to railroad customers who saw only the GM nameplate on their locomotives. Winton had become a supplier rather than an innovator, providing engines for products designed and marketed by General Motors. Over the following decades, diesel locomotives swept across North America, replacing steam engines on virtually every major railroad. The diesel revolution that Alexander Winton had envisioned in his Cleveland workshops had succeeded beyond anyone's imagination, reshaping an entire industry and eliminating technology that had powered American commerce for over a century.